Hello and welcome back to the OpShin Pioneer program. So after having had a bit of a break after the first series of videos, we now continue with the content. I'll be taking over from what Niels started, and I will have the pleasure to introduce the rest of the content to you. So we're now at the beginning of week 4, and this week will be all about kind of learning to distinguish between on-chain and off-chain code and different ways we can write code for each of them. We just start this lecture with a brief overview of what is kind of the role of on and off-chain code and how we can implement them. Okay, so what do we mean by on and off-chain? And this is also quite Cardano specific, so if you used to building for other blockchains, things might work a bit different. But in Cardano, we distinguish between code that runs on-chain and off-chain. And the on-chain code is basically what encodes the smart contract logic. So you write basically the conditions under which a transaction would be valid. And this is what will be run on the node when it verifies transactions that are stored on the blockchain. But then this only basically checks the conditions under which the transaction would be valid. But building the transaction itself is another step, and this is done off-chain. So the code that constructs transactions is what we call off-chain code, and it could run basically in the user's front end, for example, or also on the service provider's server. And this would build a transaction that is then submitted to the blockchain, where the node would check via the on-chain code whether this is a valid transaction. Okay, so why is it a good idea to decompose the code like this? Why was this choice made in Cardano? So when we think about on-chain code, we really want it to be somewhat minimal. So because it's expensive to run code on a blockchain, because it might potentially have to be run by many nodes to somehow reach the consensus on the chain. So we want to really keep the execution costs as low as possible. So this is why we basically only encode the minimal conditions that we need for our logic in the on-chain code. And then we outsource everything else to the off-chain code. So the off-chain code would also have, of course, access to the user's wallet and so on to see how to construct the transaction exactly. And so we can take care of all of that off-chain to only have really the minimal logic running on the chain. So next we want to give a kind of an overview of the compilation pipeline for the on-chain code, and also compare the way it is done in Bluetooth versus in OpShin. So here you see this pipeline for Bluetooth. And yeah, the idea, as in many or all the compiled languages, is that we have kind of a high-level syntax with many instructions that is sort of human readable and is nice to code in. And then this needs to get compiled down into some simple language with few instructions that is like somehow easy to understand by the computer, but the human would not be able to code in it, right? And here there's also like 3 different intermediate steps that we go through when we compile the code. I don't want to go too much into the details, but basically with Bluetooth you code in this kind of subset of Haskell, and then as the first step is kind of part of the standard Haskell compiler that compiles it into this GHC core language. And then there's something close to that, which is kind of Bluetooth specific. This is Bluetooth intermediate representation. And from there we go to Bluetooth core, which is suitable for doing certain compiler checks. And then we finally end up with this UPLC, which is the untyped Bluetooth core language that will actually run the node. So this would be, I mean, very hard to directly code in, and it's stored in binary, and this is what ends up on the blockchain as well. Okay, so we see these kind of 5 steps. So now if we look at how it's done in OpShin, it's actually a bit simpler. So here the high-level language is not Haskell, but now is Python, or a subset of Python, as we have seen. And of course, we still want to end up with the UPLC, the anti-Bluetooth core, because this is what the nodes can actually run in the end. And here there's like one intermediate layer, which is kind of a more human readable version of UPLC, which is called Bruthon. Yeah, I don't want to elaborate too much on this, but yeah, just you see that the compilation pipeline is somewhat simpler than in Bluetooth. Okay, so now that we have seen a bit the on-chain part, next we want to look at the off-chain part and just see roughly what are the steps that you would go through in kind of doing this transaction construction in off-chain code. And the first step when we want to build a transaction is we kind of need to know what will be the inputs and outputs and so on, because we will need to provide them as part of the transaction. So we first need to basically query this information from the blockchain. So actually, if you're familiar with the Cardano CLI, this would correspond to this Cardano CLI query commands. So actually query tip would actually just give you the current block that is the tip of the chain, but you can also query kind of for UTXOs and so on. Okay, so getting everything we need. So what the validator, the node that actually then will run the on-chain code will have access to, and this should be part of the transaction, is basically the context of the transaction, which is like if we want to mint something or spend or so on, all the inputs and outputs of the transaction with their respective values and datums, and also the redeemer. So what we want to do with the input basically, and this we need to put it into our transaction. So we first need to query it, and we can query it either by having a local node or some kind of database that is built from a chain indexer on top of a node, and maybe give some easier access, or also like some tools hosted by others, such as Blockforest API. And here actually on the left you just see basically the PyCardano equivalent of this Cardano CLI query sort of commands. So if you have a chain context in Cardano, there's this method for getting UTXOs that are at a certain address. Yeah. Okay, next let's say we have queried the information we need. And then we would want to build the transaction. So in Cardano CLI, this is the transaction build command. And yeah, basically what we just mentioned, we need to provide the inputs and outputs, and also the datum potentially, and even the script itself, unless it's basically already attached to the UTXO, and then also redeemer and collateral and so on. So yeah, we see there's a couple of different options here depending on whether the datum is actually in the UTXO or only the hash is in it. Yeah, I don't want to go so much into detail here, because actually I think if you use PyCardano, it's mostly taken care of you to some degree. So here on the left we see the PyCardano code. So we have this transaction builder object that accesses the chain context. And when we build a transaction, we basically add sort of the inputs and outputs. Actually, outputs are not shown here, but here you would add, for example, an input. Here this is a script input, so UTXO we spent from a smart contract. So then we would just provide the UTXO that we have previously fetched. We give the script as well and the redeemer. And we will see in later lectures how to actually construct like the redeemer, for example. And yeah, we add the collateral, the signature, the signers, and give validity interval, and yeah, I think we will all see this in more detail later. This is just an overview. And yeah, the final step after we have constructed the transaction is that we will actually sign it. And yeah, of course, this must somehow be done at the client's end because he has his private keys that are needed to sign the transaction. And yeah, it's Cardano CLI transaction signed, and in PyCardano it would look something like this here. And okay, now we have signed it, then we still need to submit it to the node. This is like the very simple CLI and PyCardano commands for this. And yeah, actually part of the submit procedure is also that the node basically checks whether this transaction is built correctly and could potentially be added to the ledger if nodes decide to include it in a block. And yeah, it could also get rejected, for example, if the fees are set too low or something. So this is somehow also nice because we already, before we even submit it to the blockchain, we already kind of get rid of the invalid transactions. So we're not risk somehow spending fees if the transaction is not even valid. So then in the second phase, the scripts would actually be run on the node, and the fees are used to sort of pay the node for doing this. And yeah, this is also kind of where the collateral comes in, because if for some reason the transaction should fail, it will be ignored, and the collateral is used to kind of compensate the node for still having tried to run it. Yeah, but through this also kind of distinction between on and off chain, one nice thing is that we get this kind of determinism. So we have like predictable effects. We also already know to some degree whether the transaction should pass or not, just from running it off chain. Okay, so this basically concludes this introduction lecture to off-chain versus on-chain. So in the original Pluto's Pioneer program, which we kind of try to follow here, there would be a couple of more lectures in week 4 about different ways of writing off-chain code. So there's this Kuber and Lucid frameworks that are presented. Since in this OpShin version, we kind of want to keep everything in Python because it nicely matches. So OpShin for the on-chain code and PyCardano for the off-chain code. So we will not go through these other frameworks. And of course, if you're interested, you can just watch the Plutus videos, because they would be also applicable to here if you want to write your off-chain code in another language for some reason which we don't actually recommend. But there will be one more video for the homework, and this will be the next one.